Welcome to ALD Stories, a series of conversations where we share the untold stories of atomic layer deposition and the people behind the technology. This podcast is brought to you by Beneq, the home of ALD. I'm Leah Lowell, your host for the show. Since this is our first episode, you may be wondering, why a podcast about ALD? What kinds of stories am I going to hear? And who are the guests I will be listening to on the show? Today, there are over 60,000 patents worldwide involving atomic layer deposition across a wide range of applications, including semiconductors. However, despite the amount of research and development, there are only a handful of public conferences where we can meet our fellow researchers and hear more about the work they have done. Also, if you are a material science engineer looking into ALD as a potential thin film technology, the only information you have available is the results that have been published. Oftentimes, the goals and conditions of these results are different, and what has worked in the lab environment doesn't directly translate to production. Learning these incredible insights from the early trailblazers can really help us find a better solution. This is why we have created ALD Stories. On this series, we will speak to engineers, scientists, as well as those working on commercializing the technology in notable new applications. You will hear their personal stories and experiences with ALD. We hope you enjoy these conversations as much as we will. Today we have an interesting story about ALD on glass, or to be more clear, glass used on windows. Joining me here is a colleague of mine at Beneq, Patrick Gonzalez. Hey Patrick.
Hey Leah, how are you doing? Thanks for having me in your program.
No problem. Patrick, to start off, why don't you share a little bit with our listeners about who you are, your background, and the work that you've done?
Yeah, I'm a material scientist. I got my doctorate in engineering many years ago, and I went to work directly on the semiconductors and thin films area. I currently work in marketing and sales, so I get to deal with all sorts of customers and interesting projects all over the world. These may include startups who are working on innovative applications from fabrics, semiconductors, and glass.
Speaking of glass, that's not the most frequent substrate type for ALD, is it? Yet today we're talking about a glass-related application. Can you tell us a bit more about that?
Yeah, it's not necessarily glass per se, like you mentioned, but in this case we're going to talk windows, which of course are made of glass. Now, one thing that you know is that windows are like greenhouses, and in a very summer day they trap heat, which causes a cooling costs, which are very high. Now, glass and window manufacturers are interested, of course, in offering an environmentally friendly and cost-effective solution to a cooling cost. When it comes to innovation, electrochromic windows is a big business. And you have seen this in the new airplanes, for example, the 787 Dreamliners that use these type of windows.
Yes, I know what you're referring to. These are the side windows, and typically they come with a cover, which you can pull down when you're trying to go to sleep. And they're typically tinted and dark, so that blocks the sunlight from coming into the airplane. So what is an electrochromic window from a technical point of view?
Yeah, in the simplest form, an electrochromic window is one that changes opacity. That means color from fully transparent to fully dark. Now, over the years, there are many different ways that have been studied to achieve this. Unfortunately, all these methods use an electrolyte, and the electrolyte causes a degradation over time, which means that the window doesn't go back to a fully transparent mode after it's been switched on. There are many studies. University of Washington is one that had one of the more interesting results, and they stumbled into a solution whereas using a very short pulse of a metal oxide actually fixed the problem or sort of made the opacity problem much better.
Well, that's interesting. Who would have thought metal oxide would be the solution here? Tell us a bit more about that experiment. What were they trying for?
As it turned out to be, metal oxide barriers actually seem to slow down the process. And the idea here was to actually conformally protect the electrodes in such a way that they would allow the electrolytes that cause the change in the windows to actually flow through. And traditional methods to do this were quite complicated because they were both either too thick or not conformal enough to let the electrolyte do its magic. So as it turned out to be, the University of Washington stumbled into the ALD when they found out that only a very short cycle was sufficient to protect the electrodes and solve the problem of opacity.
I think that's a great story because many of our listeners here and those people who have worked on ALD can probably resonate with this fact that ALD probably wasn't the first solution that came to mind, and oftentimes you try several different techniques before you arrive at ALD. Now, in this particular case, and they made this discovery, or someone read about this study, and they connected that with a production idea, right? So what motivated them to bring this to production? What does this mean for window manufacturers?
Yeah, one of the things that we wanted to get away from was replacing the windows that eventually were not able to fully go back to transparent mode. And this, of course, was a result of the electrode poisoning by the electrolytes. So in the financial matter, this made a lot of sense. For that matter, of course, when you look into the general picture, what we're trying to do is actually cut down on window replacement costs associated with this opacity problem over time.
So ultimately, this is cost savings in the long run for the end user, right? And also enhances the lifetime value of the glass. How did we go about bringing this to production? There are a lot of things to consider here, particularly what technique of ALD to use and why we would choose that technique over the others. Can you tell us a bit more about that?
Right. I think one of the more important things is to meet the cost associated with manufacturing these windows. And there are basically two ways of accomplishing this, two ALD techniques, if you will. One of them is a temporal ALD, where we put the chemicals, we let it sit there for a little while, and then we purge them and repeat the cycle over and over again. It's not ideal to do this continuously because the throughput it's not as good. A better way of doing it, of course, is this spatial ALD. And in that case, the way it works is there are different chemical zones that are continuously flowing chemicals. And the difference here is now the substrate doesn't have to wait for purging and pumping, if you will. It simply travels through the different reactive zones, which makes the throughput considerably higher.
Okay, that makes sense. So we chose to start the production with spatial ALD thanks to the throughput advantages. What were some of the challenges there?
Right. We had shown in the lab the ability to do spatial ALD on samples of about a millimeter in thickness. The interesting thing now is that the project really required working on a glass sandwich that was considerably thicker, something on the order of 20 millimeters.
Wow. Yes, that's much thicker.
So, yeah, that presented some issues that we had to work through.
What about precursors? That's also a major factor in the production planning. That in the case of ALD, that has to do with material costs as well. So, what were the precursor options you had available to you at that time?
Going back to what the University of Washington had explored, there were two options that were the best candidates to address the issue of preventing the poisoning. And that was either aluminum oxide or tantalum oxide.
Interesting.
Now, aluminum oxide is well understood. We had a lot of experience. Every ALD scientist's favorite oxide is aluminum oxide. And not only that, we had different machines to do this. So there was an option for the customer to do this on different machines. And we could really make it work in a relatively short amount of time. The hardware for aluminum oxide was readily available and ready to go. Mm-hmm. And we felt that this was the logical way to start with a process that was well understood.
That's clear. What about tantalum oxide? What were the considerations there?
Right. So tantalum oxide was the other option. And the thing about tantalum oxide is it's a very stable product. It has a high dielectric constant, high refractive index. So it's really found a niche, especially on optical application, which is what we were dealing with in the most basic sense. For tantalum oxide, though, we needed some special precautions, if you will, simply because the precursor itself has a somewhat lower vapor pressure, so we needed a different delivery system. And that was not ready to be taken into consideration right away. Really, the final decision in which what would be the final solution to this had to take into account a couple of things. One of them, which one gave the best transition from fully clear to fully dark, and which one did so on the shortest amount of time.
Okay, so at this point, we decided to start the production on spatial ALD and using aluminum oxide as it is a better known process. In addition, you also mentioned the thickness of the substrate, being the window glass is much greater compared to our previous tests. Did that lead to any particular challenge in the production process?
Obviously, when you're dealing with thicker substrates, the ability to keep the reactive gases from escaping becomes a much greater problem. So now we were faced with the fact that in order to do this, we would need to figure out a way to keep the gases from escaping. The other point that needed to be solved at one point or another was that it needed to be done in some kind of production line, so the conditions had to be done at atmospheric pressure. And that complicated the situation even more.
So out of curiosity, what were the expectations from the project stakeholders on the size of the production? How big was this thing going to be?
During the initial conversations, at that point, the cost for photochromatic windows was running around $100 per square foot. If we were going to successfully integrate spatial ALD technology, the calculations was we should be able to bring the price down to $25 per square foot.
Did you say 100 to 25?
Correct. So It was a significant savings. The initial demand for this particular technology, we thought, was hundreds of thousands of square meters per year. If everything worked okay, and the acceptance in the marketplace was there, the calculations, or forecast if you will, was going to grow to millions of square meters of glass.
Wow, that's really ambitious.
Indeed. And with this, it would actually require for us to have in production 4 large area spatial ALD machines roughly of the size of 4 meters in length, but by 2.5 meters in width. So quite a big machine.
And the output just sounds huge. It sounds like enough glass to cover an entire block of office building and more. And what tools did you need to support that size of production?
Right. This is when the project gets even more interesting because there was pressure to show the technology to work immediately. And
as they often happens, in these new innovative projects.
So we made the decision with the client that we would work as quickly as possible to demonstrate the concept and tackle the issues with spatial ALD later on in the project. So we made a last minute decision to actually switch production to a different ALD platform. We were going to do this on a batch temporal ALD tool.
Oh, so we switched to the temporal method in the end.
Correct.
Okay.
Now,
because of the time pressure.
Correct. And as we had mentioned, the temporal ALD is not as quick as spatial ALD.
Of course.
And to make the throughput really work, we would need some kind of preheating tool such that we would avoid cycles associated with heating the machine to the required temperature. Now, eventually, to meet the most aggressive forecast, we would, of course, eventually need to transition to spatial ALD.
Thanks to the inherent throughput advantages of spatial ALD, right?
Correct.
It sounds like the project didn't work out. What were the main reasons here? Was it because we were rushed and just you can't make this kind of last minute jump to a different ALD process? Was that it?
Yeah, we during the test, the test phase of the concept, you run into some very interesting issues that we hadn't sort of forecasted. One of them was that there were some slight differences in the uniformity between the spatial ALD process and the batch process, and they gave somewhat different results over the large area. And we really we basically ran out of time studying what was causing that slight difference in uniformity. The other thing too that
so the batch result was not as good as the roll-to-roll spatial ALD that we provided before.
Yeah, that turned out to be in terms of uniformity. Issue. Yeah. Okay. Now, let me just say that both results were equally good, but the customer at this point, as part of science, you really want to know what's causing the difference, so you know exactly what you're dealing with. But right. In this case, we just didn't have the time to explore that. The other thing in production that you never think about was that the process with doing a batch system, if you will, was entirely different and required a completely different setup with robots to move things from the oven to the batch system. And that sort of would change the entire production process as it was originally envisioned. Finally, something that had really nothing to do with the technology itself was the ability to test the samples. And that's something that was largely outside our, let's say, we couldn't really affect that. And that's simply because we were sort of held up into getting enough samples to test. Without having a continuous supply of these samples on a regular basis, we were just sitting there waiting for the samples to be tested and to arrive in our facility, run them to the ALD, and then send them back to the customer in another country. and that just took an unnecessarily long amount of time.
So we kind of underestimated the amount of time testing was going to take, and also didn't really plan for the exchange of samples and as part of the project.
Correct. The customer in this case was going through a process of very quick growth. They had a lot of things in mind. They were very technically savvy, but it turned out to be that they were not manufacturing savvy, if you will. In other words, the details of actually making decent samples for us to test and having the ability for us to test them quickly was not part of their plan, if you will. It wasn't planned as carefully as it should have been done.
I think those are universal lessons and insights we can take away from this example. It was a daring try to apply ALD in a place where no one's looking at it before. Having said that, I think things you touched on here, such as being manufacturing savvy versus just technology savvy, really speaks to a lot of the reasons why a lot of similar projects failed as well. So does ALD have a place in the future of glass? Would you say that despite this setback, someone else might actually eventually succeed in bringing this to production?
I think definitely yes. I think that spatial ALD is really the way to go. However, there are issues related to manufacturing this on a large area and keeping the gas confined and solved in a practical way that is not entirely too costly is something that needs to be worked on. And until that gets solved, then that's not going to be financially feasible to do it this way. Also, something that goes along with this is that the manufacturing price needs to really come down to a more competitive level to match other options. ALD is the preferred option, but there are other ways of achieving this that until we get to the point that we can do this in a large scale using spatial ALD is going to be hard to compete against.
Is that a factor of precursor costs, material costs, or is really the setup, it goes back to the setup factor in manufacturing again?
I believe it's more on the order of cost associated with gases and chemicals. If you're right. Going to this in a large area and you're going to do this on atmospheric pressure, then you're going to have to spend a lot of time, money, and effort in keeping those gases from escaping and having a controllable process.
Right. We're talking about that. Yeah, that's a key engineering challenge to solve here.
That's all we have time for today. We'd like to say thank you to our first-time listeners for supporting this show. Please stay tuned as we have some very exciting new guests over the next few episodes. You're listening to ALD Stories with Beneq, the home of ALD. To stay tuned for new episodes, make sure to follow us on Spotify, Google Podcasts, or Apple Podcasts. We hope you enjoyed today's show. Talk to you in the next one.